Welcome everybody to week 7, day 1. Your next programming assignment is going to be De Morgan. We'll teach you about De Morgan's law. It's a fairly easy assignment, I would say. I wouldn't get too worried about it. It'll be due next Tuesday, start of class. So, I'll be in the De Morgan directory. Let's go over what that will entail. So basically, for this assignment, you are going to have to simplify an if statement. Okay? So, yeah, let's not show the answer. So here we've got a function. And this function takes in 3 booleans as parameters. And some of the time it returns true. Some of the times it returns false. And you're going to have to make this if statement not suck. Okay? So you have to simplify this. And you're like, okay, well, what does that mean? Well, make it smaller, less typing. And so you cannot edit anything. This is a code, this is called code golf, by the way, what we're doing here. You're going to be graded on how long your answer is. Okay? And you cannot edit any of the code outside of these cut points. So what happens is that my grader essentially counts how many characters are between cut point 1 and cut point 2 and adds to it between cut point 2 and cut point 4. You cannot mess with anything outside of those 2 cut points. So it's a very simple homework assignment. All you have to do is write code here that is the equivalent of this code, and you're going to pass the correctness part of it. Okay? So, yeah, you guys understand? That's it. That's the whole assignment. It's like way easier than inventory. Okay? You're confused? You have to write a function called u that does the same thing as me. Okay? That's it. But with less typing. And you'll be graded on how many letters you type when it's graded. You can try as many times as you want. You can only edit the file between the cut points. So you can't, do anything outside of that area. I don't even think you can mess with main or anything like that. Don't mess with main at all. All you can modify are those 2 functions. So this whole assignment is literally, you should be able to do it in less than 69 characters. Okay? So you have a week to do this. Okay. You're writing an if statement that's the equivalent of mine, but with a shorter conditional. Yeah. That's it. You gotta rewrite that if statement to be smaller and more compact, because that's what we're going to be talking about today in lecture. And the Zybooks is on it as well. Okay? So, make sure you do the Zybooks. Should always do the Zybooks, but especially do it this time. You cannot put any code outside of the cut points. If you do, you get a 0. You're welcome to eliminate white space, because white space will count against you. You're welcome to use Preprocessor Macros, and I'll go over that in just a second. And don't just copy and paste mine and be like, look, it's correct, I'm done. No. You gotta simplify it. That's a requirement. Okay? So if you can come up with a simpler if statement, that's a C. Okay? Then there's lots of extra credit available based on how much smaller you can make it. So the smaller you can make it, the more extra credit you get. All right. And when you run it, let's see here. That's fine. It's not needed. When you run it, at the beginning, you'll see that it does a truth table, right? True, 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 false, true, false, true, true, false, false, right? So these are the values of I, j, and k. These are the inputs. This is the truth table that my function's giving. This is a truth table your function's giving. They should line up exactly. So you can see if your code is equivalent to mine. Okay. You can't just call my function, by the way. So, yeah. You can't call my function. So, I think some student tried that last year. They just had their me function just called u and return the result. I was like, all right, fair, but I'm not gonna allow that again. Okay, so when you run it, you can cat u.text, and that's how many characters your first u is, and u2.text is your second function. So you can see that this one is 52 characters, this one's 53 characters, and so together this is 105. And so right now it's sitting in the A territory. But all it's doing is returning false. So as you type more characters, your grade will progressively go down. So just with what we have here is not enough for maximum extra credit. You have to be smaller than what we have right now. Okay, so let's talk about preprocessor macros, because this is actually a great way of introducing it. Okay. So let's do this. Define Bob to be X, ANDed with Y, ANDed with not Z. Okay. So if we have int X bool X, Y, Z, X is equal to read. That. So we're going to read in 3 booleans, and then we see out Bob like that. What's going to happen is that it's going to copy and paste this into here. Okay. So if I have true, true, and true, we get false. True, true, and false, we get true. True, true, and false, it's true. Okay. Every other value is going to be false. So, do you see how this might be able to save you some typing? Yeah, you have to be shorter than return false. Yes. So, I'm not going to tell you any more than this, I don't think. But what this does is this does textual substitution. However, you have to put this within the cut points. So all of these letters here count against you, right? You're not allowed to put this outside of the cut points. The cut points are the area that is you, that's your code, and it counts every single letter that goes inside of there. Hashtag define the if statement. Yeah, so you could, hashtag define read to be R. Other way around. Sorry. How many characters did I just say? You know what I mean? Maybe none, because the define itself eats. If or you don't need spaces, or you know what I mean? So, all right. So you can have fun with that. All right. Okay. So now you need to know the theory behind De Morgan, and what you're going to do is actually post your stroke count here. Respond on canvas here with your final stroke count as reported by summing up the values held in view.text and view.text. I think it actually tells me, but I'll just do this here as well. Just in case. Okay. So you'll have a week to play with that. It's not a hard assignment. Okay. It's fun though. It's a lot of fun. So this is something called Code Golf, and Code Golf is a fun sport that some computer science people engage in, and so you're trying to solve problems with the shortest possible code, and yeah. That's pretty cool. Yeah. And so there's different rules for different kinds of Code Golf competitions. Ours is just counting the raw number of characters. Okay? You guys understand? Gonna be fun? Hope you have fun with it. It's always fun for me to do Code Golf assignments. Okay. So now you need to know the theory of how to simplify things. So the design books will go over some of it. The rules of Boolean algebra are some of it. You know, if you AND anything with false, it's going to be false. If you AND anything with true, it's going to be the thing, right? Like there are rules for simplifying things down. But beyond that, there is Karnaugh maps. I've heard some students called Karnaugh maps, but I don't think it's pronounced Karnaugh. So Karnaugh maps are, is it the same family? That's a good question. I don't know if it's any relation. What am I drinking? I'm drinking a latte from La Parisian. I got breakfast today. Alright, so yeah. There used to be a La Parisian kind of near our campus. The place where Boba Silog is now. Used to be one of the various La Parisians, and I would stop by there on the way to campus and get an omelet or something. Before that, it was a coffee shop called The Grind. Yeah. Okay. So, what are Karnaugh maps? Karnaugh maps are truth tables that are written differently. Okay. Same idea as a truth table, but you just kind of lay it out a little differently. And the reason why I lay it out a little differently is because you can use them to simplify if statements. They were designed by hardware people to simplify logic circuits. But guess what? Logic and truth tables and if statements are all the same thing, right? So if you can simplify a logic circuit, you can simplify an if statement. Okay. So what do they look like? They look like this. So this is a truth table that has 4 Boolean inputs to it: A and B, C and D. And ones are trues, blanks are falses. Okay. So this is a truth table that says if A is false and B is false and C is true and D is false, return true. If A is false and B is true and C is true and D is false, return true. If A is true and B is true and C is true and D is false, return false. You guys see that? Okay. So let me pose a question to you guys. If all 4 of the inputs, A, B, C, and D, are false, what value is going to be returned from this if statement or logic circuit? Same thing. If A, B, C, and D are all false, what value is going to be returned by this if statement? True? Are you guys sure about that? Yeah, it's true. Okay. What about if all 4 inputs are true? What value is going to be output if A, B, C, and D are all true? It's going to be true or false? Really? Bug landed in my coffee. Okay. Empty is false. Yeah, you're right, Tomas. Yeah, so if all 4 of these are true, then this is false. Okay. So how could we write this in software? Well, there is a good way, and there's a lot of bad ways. Okay. So the worst way that I can think of to do this is to write out every possible thing. Like I could say if A is false and B is false and C is true and D is false, that's true, right? Or let's move. So we got that one taken care of. Let's move on to the next one. Or if A is false and B is true and C is true and D is false. Or, and we can just go through these one at a time, and we will end up with an if statement that's like, I don't know, like probably about this long. Let's see, 1, 2, 6, 7, 9, 10, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it'll be about that long. Okay. Surely there's a better way of writing an if statement than that, right? What do the letters correspond to? Those are the inputs. So we've got 4 variables, 4 bools. So we got 4 booleans as input: A, B, C, and D. And that could be anything. A could be, how far, if the Target is within 15 meters. D could be if the target is friendly or not. C could be if the facial recognition system has detected Karnaugh. D could be if our system is currently ready to fire. And then based on this combination of inputs, we determine whether or not to fire the sentry gun or not. Right? Like my students trained in a neural net to recognize my face and shoot ping pong balls at it. Right? It's pretty cool. They printed out my face, put it on a popsicle stick, and moved it around, and the thing would track the face. Pretty cool. So those are some Readly students too. They did that. First generation college students. Their parents owned like an auto shop, and they tore apart like a printer, and they had a compressed air system lying around the auto shop, and so they tore apart a printer and used the thing that moved the printer head left and right, and attached the hose to it like this, and then had a camera, and the camera would report where my face is, and then it'd move the thing left and right, and then when it was lined up, then there was a valve that would release the air. They had wired in a servo motor to it to turn it, so it could turn it on, turn it off, and they had a ping pong ball in the hose, and basically once it was lined up, it went bloop, and it shot the ping pong ball. That was it. And that was all controlled by a Raspberry Pi. It's like an autonomous defense system. I don't know if you guys have ever seen, was it No Country for Old Men or something like that, where Javier Bardem is walking around with a compressed air gun and using it to kill people. It's kind of like that, except for fun, with ping pong balls aimed at me. We went along. We got along great with those students. They all got A's. Trust me. Yeah, it was a 45. But these A, that's A, and that's B. Okay. So A is the left variable. B is the right variable. Right. This one's A. This one's B. This one's C. This one's D. So we could have a really dumb and idiotic from current slide. Thank you. We could have a really dumb and idiotic if statement. But what if I told you there was a better way? Okay. So this region here. So what you do with a Karnaugh map, by the way, is you sketch it out like this, because these areas that are kind of like overlapped with different colors represent like one term of an if statement. Now an electrical engineer would say, okay, they represent like you got some logic gates and things like this, and they're using it to like simplify extra logic gates. But we're computer science people, and when I learned this in electrical engineering, they didn't teach us in discrete math, by the way. I don't know why. They didn't. But I learned this in electrical engineering. I'm like, oh, this can make much better if statements. Okay. So each one of these rectangles corresponds to like one term of an if statement. And you want to have as big a rectangle as possible, because the bigger the rectangle, the less logic gates you need, the less typing you need, right? So like specifying just this one square here, right, corresponds to me writing if A is false and B is true and C is true and D is false. So just, before we move on to the rest, so just this one square here corresponds to 1, 2, 3, 4, 5 logic gates. Okay. Whereas this whole blue area here, corresponds to A is equal to 0. Okay. So all of this could be removed with if not A. So the blue area here corresponds to A being false. Do you see that? Every square on the truth table where A is false, the outcome is true. This is the big think, okay? You see that? All those ones in common, what all these ones have in common here that are surrounded by the blue rectangle, all of them are the region where A is false. All the areas where A is true, we're not talking about. All the areas where A is false, the outcome is true. And so this is much easier to write than this, and we would have to write this for each one of these things. So that is one logic gate. If we did it this way, 1, 2, 3, 4, 5 times 8, this would be 40 logic gates. This is 1. So this is 40 times less complexity. 40 times less cost, 40 times less power. Okay, it's easier to type, it's easier to understand and debug. Do you guys see that? The blue area corresponds to A is false. Okay, so what area is the green area? Now this one is a smaller area. Smaller areas are actually more complicated, because in order to become more precise, you have to add more constraints to it. It's like if you just wanted to highlight this area here, you had to say if not A and B and C and not D. The smaller the region, the more cost you have, the more logic gates, and the more typing you need to do in code golf. So I'm going to tell you that this area here is going to be a little bit more than the blue area. So what does this green area here, which wraps around, by the way, the Karnaugh maps wrap around, what do these green areas have in common? How would you describe the green area? So can C be one of the elements of it? No. Because C is sometimes true, sometimes false within the green rectangle, so C is not worthy for our consideration. What about A? A is sometimes false and sometimes true. Nope. Can't use A either. So A is not worthy of our consideration. What about B? B is D. D is true. And D is true. For all four of these. Okay. So this corresponds to if D. And then what about B? B is false. B is false. So this corresponds to if D and not B. What does that mean for the other conditions? Well, what you do is you OR together all the conditions. So the final output of this whole thing here, the final output of this whole thing is going to be, if I wanted to write one if statement to represent this entire thing, I would say if A is false, or D is true and B is false, or now I have to do, so this is the blue area, this is the green area, I'm going to do the red area. So the red area corresponds to C being true. See how D changes within the red area? So it can't have a D in there. But C is true for all four of these. And then here we've got, it can't be A either. So B is false. Okay. So if not A, or D and not B, or C and not B. That's the whole if statement. That's the final answer. Okay. You might be able to collect across the not B's, right? You can probably say not B anded with C or with D. I think that might save you, I think it'll save you one logic gate. Okay. So how many logic gates is this total? We got one not, one or, one and, one not, 1, 2, 3, 4, 5, 6, 7. So our total score here is 7. I think the best we could do is 6, I think. Yeah, I don't think you do any better than 6. With a naive implementation, if you just literally wrote out this, ORed with this, ORed with this, ORed with this, 6, 7, 9, 10, 11 would be 88 logic gates. Oh, plus. That'd be plus 96, I think. No, sorry. 98. So the naive implementation is 98 logic gates. We can get it down to 6. So we don't need all those ifs and ors and all the wiring and all that stuff. We can simplify it from 98 down to 6. Or if we were typing this out by hand in a C++ program, rather than having 98 ands and ors and nots, we can have 6 ands and ors and nots. You guys understand? So this technique here is a really good way of simplifying if statements, which, I don't know, might be useful for, might come up. Damn it, my coffee. Order some more coffee. Just drink it. It's got like this fly just like floating on the surface. Sorry, bro. Not a fly, like a gnat. Protein. I'm not gonna drink it. Go on to DoorDash and order some more coffee. Okay, so that's the idea. Let's have you guys. Well, get some lecture. But basically, what your goal is when you're doing Karnaugh mapping is you're trying to create as large a rectangular region as you can. What is the rule for a rectangular region? 1, it must be contiguous, no gaps, no falses anywhere within it. 2, it has to be a power of 2 in size. So 1 by 1, 1 by 2, 2 by 2, 2 by 4, 4 by 4, 4 by 1, 1 by 8, if you have an even bigger one. Those are all allowed. 4 by 4 is allowed. 4 by 2 is allowed. Okay? The dimensions have to be a power of 2 because they correspond to one of these variables being true or false. Okay? And you want to make as large a rectangle as you can, and you want to have as few rectangles covering the truth table as possible. That's the rule. So let's see here. Cup of joy. Let's see if they're open. No, that's the Clovis one. They're closed. What is this? Tuesday? It's a conspiracy by the big fly lobby. Keeping me out of my coffee. Okay. So, yeah, not A is half the map, but A ANDed with B, ANDed with C, ANDed with D that's one spot. So it's a bit counterintuitive. The more logic gates you use, you actually specify a more and more precise area on the map, which is not good if you can do a more broad and general solution. Read a D&D campaign about the fly, the caffeine fly. Got so caffeinated it ascended into the celestial heavens. When I order coffee. Okay, so everybody take a look at this and tell me, and X's by the way are don't cares. And so if you have a don't care, you can either include it in a map or you can not include it in a map, whichever makes your logic easier, right? In this case, we want to create contiguous rectangular regions that are powers of 2. And so here it's advantageous for us to include it because it lets us make a bigger rectangle. And here it's advantageous for us to not include it because it's not really contiguous with anything else. And these things can wrap around too if you have to. So what if you had to write an if statement for this? It's the same layout as before. If you had to turn this into an if statement, go ahead and type it onto Discord now while I try to desperately find a place that will deliver coffee to me. Pause. And we are back. So coffee's been ordered from Boo Bean Bakery and Cafe. I've never tried them before. Let you know how that goes. In the meantime, I got some chai. Not bad. Okay, so we got two rectangles, so there's going to be two different clauses that are going to be ORed together. So that's something I probably should mention. Each of the rectangles is going to be a bunch of variables ANDed together. And that's and makes it more and more precise. And then when you want to add things together, you use OR, right? So we're going to OR that region with that region, and the regions are defined using ANDs. So the first region here, the square on the left, corresponds to A being false. Okay. So on the left, so it's going to be if the first clause is A is false and D is true. You see how C changes like that, so it's not C, so it's A is false and D is true. And then we're going to OR that with this rectangle here, which corresponds to C is false, D is true. So when C is false and D is true, that's that whole thing there. A and B change, yeah. So ORed with not C, ANDed with D. And then we could probably collect this as well. Let's see here. So we're at 1, 2, 3, 4, 5 logic gates right now. We could probably say if not A ORed with C, ANDed with D. Take it down to 3. Wait, we got an OR in between here, so that'd be an ORed with D. So we could collect the not A and the not C, or it with D, and that's 4 logic gates, but then this is De Morgan's law, and De Morgan's law can convert that into not A or with C. So that would be my solution to that is 3 logic gates. Instead of worst case would be, it's roughly 8 for each one, so about 50-ish, somewhere around there. Because they have to be ORed together as well. So instead of 50, 3. It's pretty good, right? Let's see, did you guys get it? Not A ANDed with D, not C ANDed with D. That looks correct to me. If not C ANDed with D for the long triangle, yeah. If Corrente is editing his, yeah. Okay. Not A or not C ANDed with B ANDed D. Yeah, the B shouldn't be anywhere on there. Because when B is true and false, yeah, there's nothing in here that corresponds to B. Okay, so let's ditch that. The answer it says here is not A ANDed with D, ORed with not C, ANDed with D. But I think we could do a little bit better than that. Yeah. Basically, the Karnaugh map gives you a good simplification, and then you can apply the rules of Boolean logic to further simplify if you want. It's a great way of reducing redundancy. When you've done enough of these, then you can start internalizing those rules. And like you notice, like when I look at if statements, I'm like, yeah, you could rewrite it this way. And that's one of the great benefits of this class. So let's do a worksheet together. I'm not giving worksheets because we're not in person, and just doing digital quizzes is easier. So that means I've got some material that we can use to practice. So if we go into the files section here, we can find there is worksheet probability statistics, set theory, counting, and Karnaugh. All right. I probably have it just on my local thing here. Yes, there we go. Okay. So let's run through some examples. There we go. Write a truth table for A NANDed with B. Can I write on this? Ah, cool. Inking works. Nice. Okay, so what is a truth table? So we're going to start off by writing a truth table for it. Okay. What is the truth table going to look like for A NAND B? Now we're going to fill out the truth table instead of just having it handed to us. Okay. So what does the truth table look like for A NAND B? Notice this is laid out a little bit differently. Notice that the terminology is different. Notice that my last slide used an apostrophe to indicate not instead of a bar, instead of an exclamation mark, instead of the little pistol. Like, there's a lot of different competing forms of terminology, and it's really annoying. So I just use the C++ terminology. So, people on Discord, I'm waiting. Do you say 1 or 0? You can. Or true and false. It's all the same. So, how do I fill that? What's the... what goes here? Top left corner. If A is false and B is false, what's the result of A NAND B? A NAND B means you do an AND operation, then you not the result. So that's going to be true. What about if A is false and B is true? Also true. What about if A is true and B is false? Also true. What about if A is true and B is true? If the inputs to an AND gate are both true, then we get 0. So it is an AND with a NOT stuck on the end of it. So it's the opposite of an AND gate. Okay, pretty easy. Use the Karnaugh map to fill out the truth tables for this one. Not C, ORed with not A, ANDed with not B, ORed with not A, ANDed with B, ANDed with C. Okay, so let me show you how I would do this. Okay, so what region corresponds to not C? This area here. 1, 1, 1, 1. Do you see that? So if this is true, because they're all ORed together, the whole thing has to be true. I don't even need to look at the rest of these things. Because if not C is true, then that whole row is true. Okay. Then we've got not A ANDed with not B. So which column corresponds 1, 2, 3, or 4? Which column corresponds to not A ANDed with not B? What do you think? Which column? Column 1, column 2, columns 3, column 4. Which one of those corresponds to not A and not B both being true? You guys just keep typing true in the chat. I don't even know what that means. 0, column 0, false. Yeah, no, I'm messing with you. That's column 1, 2, 3, and 4. Row A and B. There you go. So not A ANDed with not B corresponds to this column here. Okay. I'm just messing with you. I knew what you were saying. So yeah, so that is that. And then not A ANDed with B ANDed with C. So this is going to correspond to a single cell. Okay. So a single celled mitochondrion or something. I don't know. So which row, which column is this? A1, B2, which spot, which cell on this Karnaugh map does not A ANDed with B ANDed with C correspond to? Just type it like bingo letters, like A7, H12. Although if you said H on this, you're going to be wrong because there's only A and B. To be or not to be. Very good, very good. Although you'd write to be or not to be, and right, something like that, right? Okay. Yeah, 2B is correct because this is the area where C is true and B is true and not A is true. So there we go. So how do we do a Karnaugh map out of this? There's going to be two, I'll just tell you right now, there's going to be two contiguous regions we're going to place over this Karnaugh map, and you can type in the chat where those contiguous regions are going to go. Alright, so you can think of it as like one of those carnival games where they give you like a figure and you've got to place these things like over the figure to cover it up exactly. To be or not to be is true. Yeah. To be or not to be, that is the question. True! Right. Very good, very good. So Karnaugh this up. Karnaugh map it up. Where do the two contiguous regions go on here? Remember, they have to be powers of 2 in size for both the row and the column. So 1, 2, or 4 in either dimension. Can't do a 3. Although 3 I don't think matters on this one. Anyone? Yeah, we got more. I'll pause the recording now. Let people think about it. It's not immediately obvious to us where the redundancy lies. Right, we've got, you're looking at some junior programmers' code. They wrote this big if statement here. You're like, there's probably redundancy in there. I just don't, I don't know. There's like a not A here, and but that's a B and a A. And I don't know. Like your Boolean powers might fail you. And so one really nice way of simplifying these things is by you take these things, you translate them, like not C corresponds to that row, and not A ANDed with not B corresponds to that column. And what you do is you just put it onto a truth table. Karnaugh map is a truth table. And then you simplify. And so there's two regions here. One is this one, there. And that corresponds to not A. So we'd write down if not A. And then the other one is this region. Now some people might say, oh, well, we should just put it here, right? And that's wrong. But we've already covered these, I know. And technically this is going to give you a correct result, but it's wrong if you're trying to simplify, because bigger maps are simpler. And so can you have overlap? Hell yeah, because you're ORing them, right? You're ORing things together. And so you want to have as big a map as you can. And so this corresponds to if not A ORed with not C. And then that's, this whole thing here is this big old if statement with like 1, 2, 3, 4, 5, 6, 7, 8, 9 logic gates in it, or logic operators if you're in software world. This one's got 3. So it's 3 times simpler. So you just take an if statement, sketch it out like this, and then draw rectangles, and then turn it into an if statement. Okay, and you could probably simplify this down to if not A ANDed with C, using the power of De Morgan's law. Okay, so you can collect the not and save one more logic gate. So this is 2. Pretty good. Yeah, it's a really good skill because people write bad if statements all the time, or even maybe not even bad, but just like needlessly complicated. Let's say. So we're just finding out what's true and see if we can make a smaller. Yeah, these are equivalent. These are this if statement here and this if statement here and this if statement here. They're all equivalent. They're all logically equivalent. If you drew out the truth table for them, you get the same results. But if you tried making a circuit for this, if you had a circuit A, B, and C, and so this circuit here has a NOT gate coming out of the thing here, and then A has a NOT gate and B has a NOT gate, and then these two things get ANDed together, and then that gets ORed with that one, and then we're going to OR the result of that with not A ANDed with B ANDed with C, so we're going to pull this over here, not A ANDed with B ANDed with C, so that, and then that all gets ORed together like that. So here's the circuit diagram for this if statement here. So it's not C ORed with not A ANDed with not B, which is that chunk up there, ORed with not A ANDed with B ANDed with C. That's your output. Okay? It's not a 0 output. Okay. So that's the circuit diagram for what we started with. By using the power of Karnaugh maps, we can get rid of B entirely and just have A and C, right? And we can toss it into a NAND gate. There we go. That's it. So all this is a very, very complicated way of doing a NAND. It's the same. It's the same. This and this. It's the same. Okay, 1 logic gate instead of 3, 6, 7, 8. Okay. Or if you're doing code golf, less typing. Or if you're just a software engineer, you're writing a simpler, easier to understand if statement. You're writing if not A and C. Okay. Yep, so there you go. Okay, so let's do another. Use a Karnaugh map to fill the truth tables in for this one. So what area corresponds to A ANDed with not A? Which area has a column where both A and not A are true? Not seeing that on the map anywhere. Where is it true that both A and its opposite are true? What do you think? For the first one here? Can't happen. Cross it off. Cross it off. It's a contradiction. None of the elements here will be true due to this term there. Boom. Easy. Next one. B ANDed with A. Which column? Again, we'll do column 1, 2, 3, 4, row A, row B. So, what does B ANDed with A? What does that correspond to? Dre. Very multicultural computer science department here. Got Aaron, who speaks Mandarin. Parente speaks German. various people taking Japanese also. Aber nicht so gut. Should listen to more Rammstein. So yeah, so this is column 3. Column 3, not 3A. Because B ANDed with A, that's true if C is false. B ANDed with A is also true if C is true. Right? You see that? So B ANDed with A is actually a column. It's the entire column here. This is the column. Look, this is the column for A is true and B is true. Right? That's literally what that column means. That column is the A is true, B is true column. Okay. C doesn't matter. Okay, now we're going to add in B ANDed with not A. So which one is B ANDed with not A? A is false, B is true. Which column is that? 2? Okay. A is false, B is true. Okay, so boom, boom. Simplify. Oh yeah, and the last thing here is a contradiction as well. So, yoink, yoink. Simplify. Write an if statement corresponding to what we have here on our Karnaugh map. Yeah, the last one crosses off also. It does not contribute anything to the truth table because it's a contradiction. There's no spots on the truth table where both C is true and C is false, right? Just like there's no place where A is true and A is false. Like, no. Okay. So we throw a square around this area here. And this area here corresponds to, it's not going to be C, it's not going to be A because A is true here, A is false here. This corresponds to B being true. So yeah, so this whole if statement here simplifies down to if B. Now they're not always going to simplify down this nicely, but look, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 logic gates. Now this is our circuit. Just wire up B to the output. That's it. All the logic gates are gone. You just wire it up. One wire. Okay. I wonder why this isn't taught in intro classes, like like C-Sci 40 or something like that, or something like that. It's discrete math. Okay. Now, last one, we'll take a break. Again, I will write out the row A, row B, column 1. No, I don't want to cover up. You guys know how it goes. 1, 2, 3, 4. Okay, for the first one here, A, B, and C, which cell does that correspond to? A is true, B is true, C is true. 3B. A, B, C. I would concur. Okay. Ordered with A ANDed with not B ANDed with C. Which cell is that? You can just write 3B. Yeah. You don't have to disambiguate from rows and columns because we got letters, we got numbers. Okay. So A ANDed with not B ANDed with C. 4B. That's also correct. Okay, what was Sherlock Holmes' address? (221B). Okay. Okay, what is so we got that one done, we got this one done. Okay. What is A ANDed with B ANDed with not C? Which cell does that correspond to? A ANDed with B ANDed with not C. So A is true, B is true, C is false. Okay. 3A. Okay. Next one, A is true. So that one's done. Okay, so A is true, B is false, C is false. A is true, B is false, C is false. It's 4A. Good. Next one is A is true, B is false, C is true. What do you guys got? Will they ever have in them A and with B or C? No. The way that these things are laid out is that they're ORs of ANDs. So each AND defines a particular contiguous region, and you OR them together to kind of like set union, you know, the results of all the ANDs. This is a particular way of writing Boolean logic. The other way you can write it is the ANDs of ORs, right? So you can say OR A ORed with B, ANDed with, you know, A ORed with C, ANDed with, you know, D ORed with A. You know, so there's these two different ways of writing Boolean expressions that are kind of standard. And for Karnaugh maps, it's really easy to just do this. Yeah. And when you get to that last step with like a De Morgan, you know, or something like that, then I'll break away from it. But basically, when doing all this Karnaugh mapping, it's always going to be a product of sums or sum of products. And yeah. So OR is kind of like plus, right? And this is kind of like multiply. Why you'll see it written that way. Okay, so for this one, we don't need it. Yeah, it's redundant. Oh, sweet. Sorry, we lost our train of thought, and we actually just wrote that term twice. And if you don't think people do that in programming, okay. So in CSI 40 especially, they'll be like, if, you know, x is equal to 1, and then inside of it, they'll have like, if x is equal to 1 and y is equal to 2. I'm like, you don't need this part, you know? Like, you've already established x is equal to 1. You're within the curly braces. You don't need that part there, you know? But they put it in anyway to, you know, I don't know, because they're learning. Yeah. That's normal. Okay, so A ended with not C. So this is going to be a bigger one. Give me the cases where A is true and C is false. This is a 2x1 rectangular region. You're getting ahead of the curve, Yoxheimer. Yeah, A is true, C is not true. It's a 2x1 region. It is on the map. You're fine. You're fine. For A, it is redundantly redundant. Yeah, that corresponds to this region right here, where A is true and C is false. It's this 2x1 region here. Yep, so we don't need it either. Yoink. Okay, simplify. What do we got? What is the answer to this needlessly complicated if statement, which had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 22 logic gates in it. Down to 0. It's just A, if A. So, again, not in real life, you're not going to simplify this much, right? But literally, this is just if A, right? But you will usually be able to shave off some logic gates, okay? So, when you get it, whenever you see, especially if there's only a few variables like A, B, and C, if you see it being like big, it's probably wrong, or not wrong, but like could be simplified because there's only so many ways you can express the relationship between three variables, right? And if it's like a big paragraph of like if statements like this, like what I was doing here was I was individually specifying each one of these spots, right? A and B and C. A and not B, A and not B and C. You know, I kind of went through one at a time and specified these things, which is fine. And then I had a couple redundants in there. Yeah, there's only so many ways you can combine A and B and C together. If it's once it gets beyond a certain point, like I immediately am just like, all right, there's Karnaugh map time, and I'll sketch it out and be like, yeah, all that could be cancel. You know, and it's not you're rarely going to get like if A, you know, but usually it'll be like if not A ORed with C or something like that. Done. So let's go and take a 15-minute break, and when we come back, we will do. Okay, no, let's do this one now. Simplify this one. I will give you 10 seconds to simplify this truth table. X means don't care. We can either include it or not include it, whichever will make for a better truth table for us. 10. Okay. If not A. Yep. Now, if we chose to exclude that, then this would turn into like if that and that, so we'd end up with like 5 logic gates or something. But as it is, we can end up with 0, if not A. Easy. All right, so go ahead and take a 15-minute break. We'll come back at 11:35, and I've got a few more of these things to do, and then I'll give you a quiz tonight, see if you can do it. And yeah, we'll go on from there. All right, pause. All right, we're back. Now, the right way to drink coffee is coffee and a splash of milk. Sugar, nah. Sugar is bad for you. Fresh coffee at the source. You just like walk up to the coffee plant, eat the beans right off the bush, eat the lid too. So eat like a coffee ice cream and just see if you like the flavor or not. Okay. So I think I've got another one on here. There we go. Okay. So I'd like for you to convert this into an if statement. So logic gates, you're going to be using them later in your career when you take computer engineering, if you take computer engineering, I guess. It's not necessarily guaranteed. So let's convert this into an if statement. Take that logic gate and make the C++ equivalent of it. I will pause the recording now. Okay, so calling that one A, that one B. The first part here is NAND. A, ANDed, NOTed. So that'd be not A and B. And that's going to be ANDed with the results of A ORed with B. So, let's do a truth table for it. All right. So, if they're both true, is the result true or false? No, this one. If they're both true, is the result true or false? False, right? Because A ANDed with B is true, NOTed is false, false ANDed with anything is false. So if they're both true, the answer is false. What if they're both false? Then the output of this is false, and when you AND it, you get false as well. What about when A is true and B is false? It's true. Because the NAND of this is true, the OR of this is true. True. And it's symmetrical, so it's the same way. So, what is this? Simplify it now. What is this if you simplify it? If you're looking at it from a Karnaugh map perspective, you're not going to be able to simplify it. The reason for that is because this is an XOR, right? This checkerboard pattern is a classic XOR pattern, so this whole thing can be simplified down to a B with the double thing here. It's an XOR gate. So that means one or the other, but not both. So the if statement in C++ would be if, it's that thing there. And then the simplified if statement is if A XOR B. Not exponentiation. Oh. Okay, let's move on to the next one. You think you guys can do this? Maybe we'll make this homework assignment. Or this one. Or this one? You guys do that one? Yeah, just simplify that down for me. Just some nots, ands, nada, nors, XOR. Yeah. Easy. Pretty simple. Pretty straightforward. Maybe you can just look at this one and figure out what it's doing. I'll pause it. I'll give you guys 30 seconds to work through the logic on this. It's not if true. It's not if false. Like look at the thing. Like the labels on it are actually telling you what the result of this is, right? So this is a three-way AND. So this is if A is false and B is true and C is true. If A is true, B is false, C is true. If A is true, B is true, C is false. Or all three are true. So these are all getting ORed together. So how would you describe this circuit in English? The output will be true if either B and C are true, or A and C are true, or A and B is true, or A, B, and C are true. How would you describe that in English? How would you do that in an if statement? How would you do that in a simplified if statement? What's your thinking on the matter? Personally, if I had to write a function for this, I'd actually take these in as ints instead of bools, and I would just do return A plus B plus C is greater than or equal to 2. Or you can write and or and or. Do you see that? If two or more of the inputs are true, it returns true. That's how I would describe it in English. If two or more are true. If just one of them is true, 0 of them are true, no. But if 2 or 3 are true, yeah. Yep. So I'd probably do that as an int because you can't add booleans. It's not really defined. Bools can either be true or false. So if you try setting a boolean to be 2 or something like that, it doesn't work. So I'd actually tell people to pass me their booleans, and then I would just implicitly convert them to ints this way. Add them together. The comparison operator gives you a bool. So if A ORed with B ORed with C, because that would be true if any of them are true, if one or more are true. And this one, it's if two or more are true. Okay, so this is a this is a circuit that will return true if two or more of the inputs are true. Yep. And yeah, and these are three-way and an OR gates, or four-way OR gate. So in reality, this would actually probably be, this would be two ands, 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 because you feed the result of one and into another and, do a three-way and, unless you have a three-way and IC or something like that. If A AND with B, or A AND with C, or B AND with C, or A and B and C. Actually, yeah, the last one I guess is redundant. No, because this one, that's an AND there. So. This is a four-way OR gate. Yeah, it takes four inputs. You see that? So if any of these four are true, the output's true. If any of these three are false, the output's false. So, yeah. So you don't have to take two inputs, but typically that's how we do it, because all binary, all Boolean operations are binary except for not. Not is, of course, a unary operator. Okay, so all right. So what's your take on this one? What's your best guess on that one? If you just had to guess, what would you guess this was? If true, no. This is actually one of the most famous circuits ever made, at least in some circles. So this is the circuit diagram for the 74181 integrated circuit, and what this is a circuit that is what's called an ALU, an arithmetic logic unit. An arithmetic logic unit is capable of doing every type of arithmetic, except for division and modules, and every type of logic in it. And there's so much overlap between addition and subtraction and all that other stuff that I don't think it does multiply either. XOR, NOR, and NAND. It does every type of basic operation other than multiply and divide, which require more. Okay. So it can run at 45 megahertz, 90 megahertz for the improved version, 143 megahertz. Yeah, and this is 4 bits. It takes 2 pairs of 4 bits, A0, A1, A2, A3. I'll zoom in, back in again. So 1, 2, 3, 4, 1, 2, 3, 4, B. And so you take in 4 bits of A, 4 bits of B, and you can add them together. And if you remember last time we talked about how there was a carry bit, it's like that both are ANDed together in the XOR then. And so this is going to give you an output of F0, F1, F2, F3, and the carry out, which is that one, I think. So this is like the carry in as well. And so basically you can hook together multiple of these things to make an 8-bit ALU, 4 of them make a 16-bit ALU, 8 of them make a 32-bit ALU. And a 32-bit ALU is basically what you have inside of one of these things. It's a 32-bit system. Except when it's not. Right now it's a 32-bit system. And so what does that mean? Well, this is what it can do. So these are your inputs, and then these are the selection pins. So they choose which operation you're going to do. So it takes in A and B, which are the inputs, and then it takes in these selection things that's the operation. So there's 4 bits of operations possible, so there are 16 operations possible. low, 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 high, low, low, high, low. And so if you pass in, for example, 0, 0, 0, 0 for the selection bits, it will invert all of the bits in A and return that as a result. If you pass in low, 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 high, it ANDs together A and B and inverts the result. So that is a NAND operation. If you pass in low, low, high, low, it knots A and then adds the result to that to B. If you pass in low, high, it returns true. Low, high, low, low, it ORs A and B together and knots the result. Low, high, it knots B. XOR with a NOT, OR with a NOT on the B, and not ANDed with B. So these are all the things it can do. And so it can do addition, subtraction, and, or, not, nor, all those kinds of things. So basically, what you have now inside of a CPU, the heart of a CPU, the thing where it actually does where it does the doing inside of a CPU, is called the ALU, and it's not that circuit anymore, but that's the basic idea of it. So you have something called an ALU inside of your CPU. This is the actual heart of the CPU. This is where the stuff actually gets done. There's a lot of stuff in a CPU. Most of it involves loading data, interpreting the data, storing data, reading from this register, writing to that register, caching, all this kind of stuff. The ALU is actually where your CPU does the CPUing. Okay? Taking one 32-bit number, you pass in, I want to do arithmetic, and then it returns a 32-bit number. And that is that. Okay? So what you're looking at here is the primitive form of what nowadays is the heart of a CPU. Okay. So you can do comparisons. Yeah. So whenever you do an add or a subtract or whatever, like there is a thing called an ALU inside of your CPU that will execute the AND, the OR, the NOT, whatever. And the reason why it's so revolutionary is because those used to all be separate circuits. You actually used to buy adders. So you get a little card, and that card had like, and it looked like little components are wired onto it and stuff like that. But basically that card would take a 32-bit number and a 32-bit number, or however many bits it was, and return 32 bits. And you would actually plug it into your mainframe. And so if you wanted to make your mainframe go faster, you could actually buy more of them and plug more of these cards into your computer. And if you didn't need a multiplier, well, you wouldn't buy one, you know. And if you wanted lots of multiplication, then you would buy more multipliers, and your mainframe would kind of figure out how many adders it had and how many multipliers it had, and it would parcel out the work to them. And so you could upgrade your mainframe. Like if it's running slow, you could do a little benchmarking on it and see, oh, look, we only have one multiplier and we're using that thing a lot. So you buy another multiplier unit. And that was how things were. They were all separate circuits. So an AND circuit would be separate from an OR circuit, which would be separate from an XOR circuit, which would be separate from the adders. And you just plug all these things in. And then whoever invented this thing must have been a genius, because he realized there was a lot of redundancy between all the different circuits. And so this does all of them. This does all the logic operations and arithmetic operations and increment, decrement, all that kind of stuff. So let's see here. So the Computer History Museum, which again we were going to go on a field trip there, and coronavirus, they have a working IBM mainframe. And there's actually IBM texts that are alive from the 1960s that, there you go. Yeah, mostly retired IBM engineers restored them. Spent 20,000 hours putting in 500 work sessions over 10 years. So, PDP-1 was the first mini computer because it was a lot smaller. Yeah, the IBM 1401 is a pretty cool experience to go in there, because these things were in the entire rooms. Like, there's a room for the computer, and IBM techs would be the only people allowed to be in there. Like, if you were a programmer, you weren't allowed to like go into this room. Like, you couldn't. This was the sanctum sanctorum, right? You could not touch the machine. You could not be in the presence of the machine. You would hand them a stack of punch cards. You'd pass them in through a window, and then they'd be like, all right, come back tomorrow and find out if your code compiled. So you had to work pretty hard to make sure you didn't forget your semicolons and stuff like that. You know what I mean? So you would hand them the punch card, and if it errored out, you'd come back the next day, and they would hand you the results of the program. That they had printers and things like that, and they would print out "Hello World." You're like, "Yay, it worked!" Or it'd print out syntax error on line 7. You're like, "No, damn it!" And programming was very different back then, right? So here's a girl typing in probably her name. So they do there. They have a program that will read in your name, and then it sends it to like this big line printer and kind of banner prints your name. It's kind of cool. And imagine waiting a day only and that's why programmers from back then are kind of like dismissive of modern day programmers. Like, they don't even check to see if their semicolons are all there. They're the kids these days. They're all lazy and stuff. You can be so sloppy as a programmer these days, because back then you really had to make sure your program was correct. And then you'd run it, and sure, there'd be a bug, and so you'd then go home and curse and type up another program, and then you had to punch the holes in the card. They had machines for that, but basically you're entering in, do an addition here, do a multiply here, store the result here, and you just kind of hope it works, and then you run it. And of course, if you're an undergraduate who's in CSI 40, your work gets deprioritized. So like, if a professor comes in and is like, hey, I want to run my program, they take my program and they put it ahead of all your stuff in the queue. And so I get to run my program, and I could just hang out because I'm a professor, right? I just pass it in like, hey, by the way, show them the magic ring, like, professor, and then they would take all of your works and make room for me at the very front. I'd hang out for an hour. They would run it. I'd be like, oh, cool. I have a bug. I need to go fix that. And then I could go back to my office. All of you would wait till the next day, because these things ran 24/7. And they did what's called batch processing. So you would wait for your job to come up, and then they would run it. And then the printers, you can see the big line feed printers here. They would print out the results. Like, that's the console out. It goes to here. And then they would have a printout, and they'd put it into a box with your name on it, and you'd pick it up the next day. Look, it worked, or dang, it didn't work. So it was a really, in my opinion, terrible way of learning programming, but programmers were really knowledgeable about, they're real careful, a lot more careful than they are today, So this here is a magnetic tape storage. So these things could advance the tape or rewind the tape, and this was your mass storage. So hard drives back then were gargantuan, 1 megabyte hard drive. Like the first, not gigabyte, megabyte. No. Here we go. There you go. So I think that's something like there you go, IBM. I think that's a 1 megabyte hard drive, if I recall. No, 5 megabytes. I'm sorry. I didn't mean to insult them. The 5 megabyte hard drive. It's like, this little SD card I got right here is like, what is it? 32 gigs, on this tiny itty bitty little thing here. Yeah. You used to have to manhandle these things. So most of the is this amusing for you guys? Because it's amusing for me. I don't know. Yeah, this is how you had to do your mass storage. And so you had to fast forward the tape and rewind the tape. And so, like, if you're going to randomly jump around, like read from, the first part of the file and the end of the file, then you have to sit there and wait. And the thing will sit there and spin for like 30 seconds. And these things were pretty high speed too. Like these were no jokes. And if something went bad, it was actually kind of funny. These things spun so quickly that if they broke, they would despool the thing almost immediately, and you'd get this giant fountain of magnetic tape just everywhere. And then some intern probably has to go and like spin the, very carefully, get the magnetic tape and wind it back up onto the thing. These things ran really fast, and these line printers also were really fast. Like, they were pretty cool. I've seen them in action. Like, we had them even back when I was in college, and those things fly. Like, those things can print so fast. It's ridiculous. They printed so fast. The friction of the paper moving through the system was such that if it just built up a little bit, like you got paper dust on there and stuff, it would actually burst into flames. And so they actually had a separate fireproof room at my college for the high-speed line printer. And what they did was they printed out every student's homework. So every time you submitted what was its name? This is a IBM 1401, but it's just a high-speed line printer. So when you submitted your programs for CSI 40, they would all get printed out. And so what would happen is your homework would go to a print server. The print server would print your homework assignment, and then the TAs would actually pick up your programs and grade them by hand. And they would circle parts of the code and be like, oh, bad commenting, bad indentation, don't like the variable name here. And that was how grading took place. And watching these printers in motion, it was utterly absurd. These things moved so fast. A fountain of paper came up out of them. Like, the paper actually shot into the air, and then it fell into a box, and it would fold itself, into this box, and it would go, shh. And if the thing ever burst into flame, then it had like a halon fire suppression system and stuff like that. It's pretty cool. It's pretty neat to watch. And I don't even think that grading that way is necessarily bad either, because having somebody actually able to mark up your code, and there's modern tools for doing that, like Canvas has markup, and there's various code turn-in systems that allow you to mark up your code. But I prefer auto grading because it would take like a week or two for you to get your homework back, because the TAs would be handed this giant box, and they would take one student's work out and unfold the paper and diligently go through it one line at a time, like, no, there's probably a bug there. I'm not sure if there's a bug because I'm not running it. I'm looking at a printout. Pretty sure there's a bug there. And if there wasn't a bug, sucks to be you. You lost the point, So, sounds like a nightmare. A little bit, yeah. The main thing that annoyed me was they would mark off for style. And a lot of professors believe it's really important to teach style and to punish people if they do the wrong style. And there's something to that. But at the same time, like, what I do is I just have my compile shell script reformat your code. So my thing just makes your code look nice no matter what. And then once your code looks nice, like, you instinctively will match your new code to match the old code. And so I just kind of teach style through the back door, as it were. So anyway, so this circuit is like one of the most important circuits, of all time. It's a history, little trip down history lane there. Okay, for this one, oh lord, not A ANDed with the result of B ANDed with the result of NAND B and C. Yeah, I don't even want to do that one. Oh lord. Ah, that's good. Good enough on that. Any questions about that? Do you think you can do a Karnaugh map if I put it up on the quiz for today? Okay. Totally. With cross out. Yeah, so don't care is useful in a Karnaugh map because you can either include them or not include them. It actually makes it's quite nice. Actually, I'd have a don't care. And so yeah, so Karnaugh maps allow you to just kind of eyeball a circuit and simplify it. And they're a real neat tool. You have your tool shed. It'll help you with the De Morgan assignment. All right. How much time do we have left for today? What, we run till 12:50 on Tuesdays. 3 minutes. Okay. All right. Well, let's continue our exploration of logic and talk about formal logic. Pink. No. There we go. Black and white. Let's stick with that one. Okay. So, Boolean logic is also called bivalent logic. You can have two different values. Trivalent logic exists, and things can have three values. For example, true, false, or don't care, right? That's trivalent logic. So, P is, whenever we talk about P or propositions, they're, in logic, we mean things that can be true or false, right? They're truth-bearing statements or propositions, or there's a lot of different ways you can say it. Basically, for example, if there's if I make the statement, it's raining outside right now, that's either true or false, right? Or is it? I don't know. What do you think? It's hot outside. True or false? What do you think? Do you agree? It's hot outside right now. Is that a true or false statement? Or is it an opinion? Is it subjective? It's hot outside? I don't know. It's 110. I think most people would agree it's hot. Temperature is an objective, number. What do you think? What about it's raining? Is that objectively true or false? You can start off logic, making you question everything. Depends on geography. I mean, I'm talking about right now. Outside of my window, it's raining. I'm making the claim right now. Right now, outside of my house, it's raining. True or false? Or is it not a true and false statement? What do you think? It's an objective statement. Okay. So, does that mean my statement, it's raining outside, must be true and false? True or false? Okay. What if it's drizzling? What if I got one drop? Is it raining? What if it's misty? What if it rained? Might still be raining, but it's just not raining right now. Like the rain clouds overhead. I'm just not happening to get any rain falling on my house. True or false? If one rain drop fell out of a rain cloud, is it raining? Yes? Okay. How long does the state of it's raining last for? Half an hour? I got one drop, half an hour. Can I say it's true that it's raining right now? Until it's not raining? Well, it was just one raindrop, so, But you said if there's one raindrop, it's raining. It's true. That was it. Like how long does the state of it's raining last for? 5 minutes? Like after it hits the ground, that's it? So when the raindrop is in flight, it's raining, but then after it hits, it's not raining. And so when it's in flight, you don't know that it's raining, and after it hits, it's too late. So you can never say it's raining and have it be true. It rained for 1 second. So when a raindrop hits, you have 1 second to say that it's raining. After that, all bets are off. That's it. There's just a time. You set a timer. During that time period, after the one raindrop hit, it's raining is true, and then cut off. It's raining is false. Break it up into 1 second resolution. Why a second? Why not a minute? We just say precipitation. I mean, that would cover the mist case. I mean, can you tell the difference between a raindrop and just other forms of atmospheric moisture? It's not rain. Oh yeah, I'll stop torturing you. So for now. So Aristotle was a smart dude. He came up with these books, which are kind of collectively called the Organon, which are sort of like the rules of logic stuff, rules of argumentation, true and false, that kind of stuff. And he's kind of the father of bivalent logic, the rules for when things are true and false. So there's three main laws of bivalent logic. First is the law of identity. True is true, false is false. If it is raining outside is true, it is raining outside is true. Okay? Makes sense? It's like in algebra. X is equal to X. Y is equal to Y. Okay? The law of identity, kind of boring. Don't really use it. Law number 2, the law of non-contradiction, which we abbreviate the LNC. The LNC. Which there's other things that mean that. It's one of the troubles, like acronyms. There's so many different acronyms, but yeah, the LNC is the law of non-contradiction. So if something is true, it is not false. If something is false, it is not true. Okay? Make sense? Something's true is not false. Something's false, not true. You cannot have both true and false for the same proposition at the same time. Pretty straightforward also. Now, controversial one, so to speak, is the, modern politics, who knows. Although a lot of the statements the politicians make aren't truth-bearing at all. And I don't mean that sarcastic. I mean, like if you make like a normative statement, like we need to do X, that's not really true and false, right? Like, we need to build an airport in Fresno. Like, it's like an opinion, right? Bigger airport in Fresno. So the law of the excluded middle, though, is that truth-bearing statements must either be true or false. There's nothing in between true and false. And that's kind of what I was getting at with my torturing review on the rain, is that that's kind of controversial, right? Like, I have an apple in my hand. Cool. I start eating it. At some point, the apple's gone. So I even eat the core and get that sweet cyanide in the apple core. Did you guys know that? Apple seeds contain a very small amount of cyanide in them. Let's say I eat the entire apple, stem included. It was true before, I have an apple in my hand. Now there's no apple in my hand. At some point, it went from true to false. And no matter where you draw that line, like one atom of apple, I still have an apple in my hand. Really? This looks like a carbon atom to me. Is that an apple? Like, how do you, like, I'm touching carbon right now. Is that an apple? Like no matter where you draw that line, it causes trouble. And so the law of the excluded middle is, like I said, controversial. So, but, whatever, we're studying Aristotelian logic. So if it's a truth-bearing statement, the statement must either be true or it must be false. And even Aristotle had exceptions to this, which we'll talk about. But like if you had something like a don't care, right? What's the truth of that? I don't know. I don't care. It's your sullen teenager response. Coincidence, you're just eating an apple right now? It's funny. Yeah, you're not going to kill anybody with the apple seeds, you know. How dangerous is an apple? You're highly unlikely to manage to eat enough apple seeds to poison yourself. So rest easy if you occasionally swallow one. So you get about 2 milligrams of cyanide. So if your body weight was about 1 kilogram, you would die. There you go. So, yeah. I wouldn't, you know, I'm not recommending you go out and eat apple seeds, but at the same time, like, people make these claims like, oh, you know, chocolate will kill dogs. Have you guys heard that one before? Chocolate will kill dogs. It's true. Bring it into the logic of the lecture now. It's true that chocolate will kill dogs. Wait, is that a myth? No. It can kill dogs. But you need to actually figure out the body weight of your dog and see. This is like, you know, because you'll just see people online. They get like really like upset. Like, don't leave chocolate out in your house. Your dog will eat it and die. So you can actually calculate how much chocolate you need to, you know, for your dog to eat, for you to be upset. So like my dog was about 80 pounds, big dog. He was a giant dog. Yeah, he's a heavy dog. Maybe if I go with a smaller dog, but you know, I'll go with one of my other dogs. Still a good dog, good sized dog. He's a Heinz special, if you've ever heard that phrase before. It's a dog that's mixed because all the different ingredients go into Heinz ketchup. Anyway, so we got here our 40-pound dog, and my 40-pound dog. At Christmas time, my grandmother handmade all of these chocolates and left them up on the kitchen counter. We're all in the living room, you know, doing Christmas stuff, and I go over there, and the tray's on the ground. The dog is lying next to it, very satisfied, smile on his face. Had consumed the entire tray of chocolates. Yep. So, what type of chocolate is probably milk chocolate? How much milk chocolate was eaten? Advent calendar, an entire advent calendar, chocolate sphere bag, gift box. Yeah, let's say like 5 of these. Yep. Calculate. Mild to moderate. Okay. So. Your dog may need to see a vet. There you go. So this is 60 pieces of chocolate, by the way, on not our bigger dog. You know, so you can actually do a calculator and find out like if you should be worried. It's a much bigger issue for like toy dogs and things like that. But like our big dumb dogs would steal, like, it's not like we were feeding them chocolate, but they would steal chocolate because they love the taste of it. And so it's one of those things. Like you'll just hear people and you just assume it's true. Right? So is chocolate toxic to dogs? Yeah, it's got some chemical in it that is toxic to dogs, but it's a matter of degree, right? And that's what the law of the excluded middle gets rid of. Again, to tie it back into the lecture here, is that it's either true or it's false. And it's like, okay, with toxicity, it's a sliding scale. Like the more chocolate you eat, the more poisoned your dog is, and the more health concern you have for it. You know what I mean? It's like a thing like this. It's a line. You know, it's not like a stepwise function where it's like he's not poisoned, he's poisoned. You know, like the reality of the situation is you have to calculate the megs per keg, the amount of milligrams per kilogram of weight, and you know, my wife does these kinds of calculations all the time. You know, when you dose drugs, you figure out the body weight, and they have more sophisticated models than that. But basically, You kind of figure out if you take this much drug and dilute it into this much body weight, this is the dosage level, and you want to make it part of the therapeutic window. There's too much, overdose. There's too little, it's ineffective. And so there's a therapeutic window where the drug works and doesn't kill you, or suffer other, consequences of overdoses. And so for some drugs like vancomycin, they have a fairly narrow therapeutic window. So vancomycin is a powerful antibiotic, and doctors aren't, oftentimes don't dose it themselves. They don't say, all right, take 2 of these and call me in the morning. For Vanco, which is, I believe, an IV drug, they could be wrong about that. Intravenous. Yeah, it's an IV drug. Okay. So, or recommended IV. And so it's got a narrow therapeutic window. And so my wife has to be like, she does the calculations and says, this is how much drug you have to give the person. And it's not, the law of the excluded middle is like, is something poisonous? Yes or no? It's like, well, everything's poisonous if you have too much of it. If you drink too much water, you'll die. Right? Did you guys know that? Like, there's these like radio DJs that like they do these like stupid contests, stupid dare contests, and like this guy won a contest by like drinking 5 gallons of water and then died from it. Not even drowning yourself. I'm not even talking about like aspirating the water. There's a hyponatremia. Give me something in English, thank you. Most common type of elite imbalance occurs in 20% of people admitted to hospital, and 10% of people doing endurance sporting get hyponatremia. It means you don't have enough salt, specifically sodium salt, in your bloodstream. Yeah, so anyhow, like people will do these like stupid dares, and they like drink these, like college students will go out and drink these giant bottles of water as a dare, and then they die. They don't always die, but it depends how much you drink, right? So, and so if you make a statement like cyanide is poisonous, it's like, I'd agree with you, but it's like, how much cyanide are you talking about? Everything is toxic if there's enough of it, right? Oxygen, if you breathe 100% oxygen, I guess you won't die, but like, you'll feel weird, side effects of it, and you probably might set yourself on fire. So, yeah, so like I said, the law of the excluded middle is a bit controversial because, most of these things are matters of degree, and the law of the excluded middle says no, true or false. Leibniz, who is a smart dude who invented calculus. Sorry, Newton, but it's true. I don't know if you guys know about the calculus priority debate, but that was a big, hot flame war that went on for a long time. Both Newton and Leibniz basically independently invented calculus, but Leibniz did it first. So anyhow, so he added a 4th law called the PSR, the principle of sufficient reason. Carnegie team Leibniz. Yeah, I mean, it's like, let me just make sure I'm not calculus priority dispute. Leibniz had published first, right? But Newton's supporters accused him of plagiarizing his unpublished ideas. Bonner consists they did it independently. Yeah. So, yeah, Leibniz published first. Sorry, Newton. I don't care that you're working on it. You snooze, you lose, buddy. So, yeah, Leibniz not only has calculus, but he also has the PSR, which is a pretty important thing. And so the PSR says that for every action, there is a sufficient reason for that action. Okay? So for every action, there exists at least one explanation why that thing happens. A sufficient reason. right? Not just like, I don't know, right? And so, yeah. So that's an optional fourth rule, and you're probably not going to see that though in most like primers on logic. Okay, so you guys understand? X is true, false is false, true is not false, and everything must be either true or false. And so with these three axioms, then we get, how do you plagiarize an unpublished work? I think he visited England. Nah, done enough digressions today. I think he might have visited England and caught wind of it, maybe? I don't know. Okay, so here's a statement. This statement is a lie. Is it true or false? Let's do the truth table on it. Kind of, I guess. So if this statement is true, the statement's a lie, and it's false. If the statement is, if my claim the statement is a lie is false, then that means the statement is true. Which means it's a lie, which means it's false, which means it's true, which means it's false, which means it's true, which means it's false. So the standard response from logicians is to ignore it. Sometimes they will try disallowing it. They say you cannot make meta statements. You cannot make statements about statements. To which people say, well, why not? You know, we say that all the time. Bob's telling the truth right now. You know, you can't have self-referential statements. Okay. Statement A says statement B is a lie. Statement B says statement A is true. Yeah, so it's a problem, and again, a lot of these problems come from the law of the excluded middle, right? Like the law of the excluded middle is the reason for this being a paradox, right? If you have these three laws, you will get paradoxes. Not just one. There's an infinite number of paradoxes that come back. And if you do things like get rid of the law of the excluded middle, or if you allow for contradictions, which a guy by the name of Priest, he's not a priest, that's just his name, Graham Priest. Graham Priest says, yeah, no, contradictions are okay. A guy by the name of Wakajevitz, what does spell that? Luke, it looks like Lucas. No. Oh, I know how to find it. If you guys ever heard of reverse Polish notation, this was like in CSI 41. I sometimes do this with my students. So you do reverse Polish calculators. 3 plus 4 was written this way. Yeah, Łukasiewicz. Łukasiewicz. That's a wa sound. So Łukasiewicz. Okay. So he said, I'm just gonna call him Luca. There you go. He said, no, you don't need that. So there's ways of resolving these sorts of paradoxes. And I'm just going to tell you guys that off the bat. Okay. So a related paradox is Russell's paradox, which in set theory, remember how we said we just kind of allow you to define a set however you want. So Russell said, okay, I'm going to define a set that's a set of all sets that do not include itself. So does it include itself? If it includes itself, then it is not the set of all sets that are not members of themselves because it's a member of itself. If it does not include itself, then it's also a lie because we define it as the set of all sets that are not members of themselves, and there's a set that exists that isn't a member of it. So it's kind of like the barber paradox where you say there's a barber in town who shaves all men who don't shave himself. Does he shave himself, right? And so, although this seems just like, haha, it's kind of fun, mild academic curiosity, it upset the entire world of math 121 years ago. Okay. I told you before about Logicomics, which was written by a former professor of mine. The notion that mathematics was on a shaky foundation, that nobody could actually explain why math was true, was a real hard, wake-up call for a lot of mathematicians. Like, we always thought of math as being the most true of all of the things, the most perfect, beautiful thing. And Russell's like, yeah, no, you don't really have any reason to believe that what you believe is true. You just kind of assume it's true. Like, all proofs kind of stop at a certain point. And they're all on a foundation of sand. And set theory is oftentimes, like I said before, used as the foundation of mathematics. Like, you can define addition and subtraction in terms of like adding things to a set or removing things from a set. And since set theory turned out to have an inherent contradiction in it, right? Like, the one thing you're not allowed is to have a contradiction, right? So if your fundamental starting point of mathematics has a contradiction at its very heart, then you got a problem. Then you got a very serious problem. And so this is more than just like, haha, fun and games. Like, all Cretians are liars is the original way this was phrased. And it was said by a Cretan. And so the question is, was he telling the truth or not? Right? And these kinds of puzzles and riddles have been going on for years. But it actually upset the entire mathematical world and caused a lot of controversy. You also have the Sorites paradox, which I already referred to. If you eat an apple, at what point is the apple not an apple anymore? And if you have the law of the excluded middle, at some point you have apple, 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 true, 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 true. You keep eating it, false. Okay, well, why is that the point at which it turns from an apple into not an apple? When there's one slice left, it's suddenly not an apple. There's one atom that if you add that atom to it, it's an apple. If you take that atom away, it's not an apple anymore. So that one atom contains the appleness. Apple, not apple, apple, not apple. Really? It's just a carbon atom. All the other things in there are carbon atoms. Why is this carbon atom special when it's just like all the other ones? Et cetera, et cetera. And so there's a lot of paradoxes that come about through Aristotelian logic. Okay. But it's the foundation for modern logic. It's the foundation for computer science. Bertrand Russell is considered one of the fathers of computer science, among other things. Philosophers love Russell and mathematicians love Russell. He was an interesting guy. He was a pacifist at a time where being a pacifist wasn't very popular. But whether or not you think that's a good idea or not, at least he stuck to his beliefs. Pretty smart guy. So yeah. So these laws are sort of the underpinnings of computer science, right? Everything's ultimately, at the end of the day, everything boils down to a transistor, and the transistors are digital, at least in our world. And if you're a musician, you're probably used to transistors and op amps being analog, which they are, but we treat them as digital devices. They're either true or false. It's either 5 volts or 0 volts, right? It's true or false. And so this is the underpinning of everything. This is the theory behind everything that we do in computer science. All of this Discord and streaming and PowerPoint and all of it boils down to these 3 laws right here. Despite their problems, it works well enough that most people just sort of pretend it doesn't exist. Pretend there's no problems with it. Okay? So that's it for today. Your homework is De Morgan's Law. I want you to have fun with it. I want you to really look at the hashtag define things and go crazy, go wild. See, there's a lot of off-the-wall ideas you can come up with that will reduce the character count below 100, right? Like, the reason why 69 is the highest score isn't because of the meme, value of it, but because the top student last year, I think, was 67. I think one student did better than that, but cheated. Not like cheating, but like they modified the code outside of the cut points. So yeah, so use your powers of, work through it's just 2 if statements, just put them into a Karnaugh map, solve them, simplify, start from there. Okay. What's the lowest? I don't remember off the top of my head, but I think he got it down to like 30 characters, but again, that was kind of cheaty. Like 67, I think, was the lowest last year. Other than that, I'd have to look at my stream from last year, but somewhere below 69, a couple letters below. So, I don't want to give you any more hints than that. I want you to figure it out yourself. Is the lowest possible 53? Maybe. Yeah. I don't know. What's 53? Why 53? That's what yours is compared to? No, that's just the starting. So it's 52 in the first one and 53 in the second one. I'm not talking about, by the way, 53 for one. I'm talking about 67 for both combined. Not one. Both. Yeah, 52 plus 53 is 105 characters. So as of right now, your code is, with nothing in it is 105 characters. So, again, there's clever ways. Play with it. Use your knowledge of C++ to compress and reduce. That's extra credit points. Yeah, I mean, if you just do the assignment, that's a C, but what's the fun of that when there's extra credit available? So, can we change the input to ints and it still work? I think so. Try it. I don't know. If the code compiles and you get the right answer, it's correct. So that would be a way of saving some letters, right? If the, I think the output would break if you change the output to an int. It's going to see out as a integer, and I've had students do that before. Like they casted this to a bool in main. Can't do that. Can't do that. Can't touch anything in here. What you got's what you got. So yeah, if you change that to an int, it'll output as a number instead of true or false. So, but yeah, there's ideas. The name of the functions are already pretty small. You can, I don't know. I don't want to give you any more hints. It's a fun assignment. All right, so that's it for today, and I wish you all a wonderful coffee day, where I'm about to go get the coffee that I DoorDashed in. All right, see y'all next time. Stupid bug.